Hello dosto, I'm Abdul with you with a video about relation between CP and CV, which is most important topic in thermal physics from first law of thermodynamics. Let's start the video. General relation between CP and CV. To find the relation between CP and CV, the following two definitions should be kept in mind. First, specific heat at constant pressure, which is CP. It is defined as the amount of heat required to rise the temperature of 1 mole of a gas through 1 degree Celsius when its pressure is kept constant. It is denoted by Cp and given by Cp equal to dq by dt at constant pressure. Second, specific heat at constant volume, Cv. It is defined as the amount of heat required to rise the temperature of 1 mole of a gas through 1 degree Celsius when its volume is kept constant. It is denoted by Cv and given by Cv equal to dq by dt at constant volume. We have already discussed the definition of Cp and Cv. Consider 1 mole of an ideal gas contained in a cylinder provided with a movable piston of area A. Let P, V and T be the pressure, volume and temperature of an ideal gas respectively. Let the heat supplied to the gas be dq. A weight is placed over the piston in order to keep the volume of gas constant. The pressure and temperature of the gas changes to P plus dP and T plus dt respectively. In this case, dq is used to increase the internal energy du of gas, but the gas does not do any work, that is dw equal to 0. Applying first law of thermodynamic, which is written as dq equal to du plus dw. Now putting the value of dw in this equation, we get dq equal to du plus 0, which is equal to du. And for some time we have discussed the definition of Cv, which is equal to dq by dt at constant volume V, from where we get dq equal to Cv dt. Putting the value of dq in this equation, we get du equal to Cv dt. Now the weight is removed from the piston. The piston moves upward through a distance dx as described in figure. So the pressure of the gas is equal to the atmospheric pressure P. Due to the expansion of the gas, its temperature decreases. Now the dq dash heat is supplied to the gas such that its temperature become T plus dt. dq dash is used to increase internal energy dV of the gas as well as external. Now the dq dash heat is supplied to the gas such that its temperature become T plus dt. dq dash is used to increase internal energy dV du of the gas as well as external work done dW in moving the piston upward. That is dq dash equal to du plus dW, which is mentioned as equation 2. Since during the expansion there is no change in pressure, therefore we can write dq dash equal to Cp dt, which is mentioned as equation 3. Again, we know that work done dW equal to force into distance. We can write force equal to pressure into area into distance. Pressure is denoted by P and area is denoted by A and distance is denoted by dx. So we get PA dx, which is equal to P dV. A dx equal to dV. Now putting the value of dq dash, du and dw in equation 2, we get Cp dt equal to Cv dt plus Pdv. But for an ideal gas, Pv equal to RT. Differentiating both sides, we get Pdv equal to Rdt. Putting the value of Pdv equal to Rdt in equation 5, we get Cp dt equal to Cv dt plus Rdt. Taking this term in left side, we get Cp dt minus Cv dt equal to Rdt. Taking common dt, we get Cp minus Cv equal to Rdt. Now dividing by dt in both sides, we get Cp minus Cv equal to R dt by dt. This term and this term get cancelled. This implies Cp minus Cv equal to R, which is the required relation between Cp and Cv.